Yeah, hi. I'm Subhajit. As you know, that I have been assigned as the TA for this course, and this is just week 0. So this is just a sort of a dry run before the actual course starts. And thank you for joining. By the way, am I audible?
Yes.
Yeah. Okay. So I have taken some contents from the week 0 assignment, and let's solve it. Yeah. Okay. So hopefully you can see my, you can't see my screen, right?
No, you haven't shared yet.
Oh, yeah. Yeah, probably now you are able to see.
Yes.
Okay. So yeah, you can see the Jamboard, right? That I'm sharing. I mean the screen at least.
Yes.
Yeah, thanks. So let's just solve some of the problems. Yeah. So this is a very simple problem, and it's concerned about computing dimension of a very known vector space. So let me just read it out. That suppose V denotes the vector space of all 3 cross 3 real matrices, and as a vector space over R, it has dimension 3, 6, 9, or 27. Now you know that V is taken to be M3R, and the you can check this, that the matrices E, I, J, where I and J run from 1 to 3. Now what is Eij for I and J between 1 and 3? So Eij is the matrix with the ijth entry. So how should I write it? So yeah, Eij is the matrix whose, okay, the ijth entry is 1 and all other entries are 0. So you can check that all these matrices, as you understand, they are precisely 9 in number, and all these matrices together will form a basis for V. So that's easy to see, and the point is that so you get that 9 should be the dimension, because the number of elements in the basis is precisely 9. Yeah, so this is not difficult, this is easy. So now we come to the second one. So again, assume V is the set of all 3 cross 3 real matrices. So V is M3 cross 3 M3R, but with an added condition that these matrices should have 0 trace. So we take all A in M3R such that the trace of A is 0. Yeah. So now we again need to this is a vector space. It's a subspace of M3R. We need to compute the dimension of this vector space over R, right? So you can, what you can do is you can just look at any particular such matrix. So you have entries here, 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 here. So you are allowed to choose these elements independently, just that you have an added condition that these 3 elements, when entries when added, should give you 0, which means that you cannot I mean, of all these 3 elements in the main diagonal, you cannot choose, I mean, one of the elements is dependent on the other 2, right? So you just are not allowed to choose one element. That will I mean, that will be determined by the other 2 elements in the diagonal, right? So I mean, yeah. So So then the number of elements you can choose freely is precisely 9 minus 1, which is 8, right? And hence the dimension should be precisely 8. Now the way I solve this problem is a bit unconventional, because usually you want to compute basis for this vector, a basis for this vector space, and indeed you can. It's just the same way, but maybe this way is easier. I mean, it's not a full argument, but yeah, it's easier. You can check. I mean, yeah. So let's go to, I don't want to waste time in this, so let's go to problem 3. Yeah. So this is about solving a simultaneous system of linear congruences. So it says that you are given a system x congruent to 3 mod 4 and x congruent to 0 mod 6, and you are asked whether this system has a simultaneous solution or not. Okay. Now it's easy to see that it doesn't. The answer should be no, but let's see why. So assume indeed that there is a simultaneous solution to this system, and let's denote this denote the solution by x. So you have x congruent to 3 mod 4, which gives you that x minus 3 is of the form 4k, that is 4 divides the difference x minus 3, which implies x is 4k plus 3, right? And if you just plug in this in the second one, so you get 4k plus 3 is congruent to 0 mod 6. Now the point, this therefore implies that 6 divides 4k plus 3, right? And which in turn will imply that 3 divides 4k plus 3. Now I mean this is a contradiction, right? Because
Anyway, 4k plus 3 is odd. 6 cannot divide it.
yeah, anyway 4k plus, yes, 4k plus 3 is odd, and therefore 6 cannot divide it, right? Yeah, that's a better solution. I mean, yeah, that's a solution. Yeah. So 4k plus 6 cannot divide 4k plus 3 because it's odd. So this is impossible, and hence the answer is no. Now, and it's not very surprising that the answer can be no, because you see, you are taking modulo 4 and modulo 6, right? So essentially what this means is that this map Z2 Z4 cross Z6, this particular map which sends any integer n to the respective classes mod 4 and mod 6, this map is not surjective. In particular, 3, 0 is certainly not in the image of this map. Now it's not very surprising, because if you just recall the Chinese remainder theorem, then the Chinese remainder theorem precisely says that this particular map, I mean just a special version of the theorem will say that this particular map is surjective if and only if the modulos, I mean the whatever it is called, I mean if and only if this, let's call it m and let's call it n, if and only if m and n are relatively prime to each other, right? So clearly 4 and 6 are not relatively prime here, so this map is certainly not surjective, and it just happens that 3, 0 is not in the image, right? Yeah. So if you were stuck with something like, if you were asked to compute, let's say mod 4 and mod, compute a solution mod 4 and mod 7, then clearly 4 and 7 are relatively prime, and hence this system will always have a simultaneous solution. It just happens there is no solution in this situation. Yeah. Yeah. So the next problem, by the way, do you have any questions? Hello?
No.
yeah, so yeah, so the next question is a bit, I mean, it's essentially from combinatorics, and it is asking about the number of ways of seating 6 people around a circular table. And I mean, that's again very easy, because you know this, that the number of ways of sitting or sitting n people in a circle is precisely n minus 1 factorial, so you get 120 as the answer. And yeah, I mean, this is again not difficult to, if you just want to compute by compute more more if you just want to compute it uh, from scratch without assuming any formulas or anything, so you can just take this, you can just consider this, that so there is one way, I mean, the number of linear, yeah, okay, so just see that the number of linear arrangements of 6 people is precisely 6 factorial. So so one circular arrangement corresponds to uh, 6 linear arrangements, right? Basically what I'm saying is, if you arrange A, B, C, D, E and F in a circle, I mean in a line, then this is one configuration. If you just push A back to back at the end, then you get another configuration, B, C, D, E, F, A, and you continue and you end up with I guess F, right? So F, A, B, C, D, E, right? Yeah. So you have total 6 linear arrangements, but all these arrangements will will correspond to exactly one circular arrangement, right? So yeah, so 6 linear arrangements give you one circular arrangement. One linear arrangement therefore will give you, I mean, yeah, 6 linear arrangements give you one circular arrangement, and hence 6 factorial linear arrangements will give you 6 factorial over 6 circular arrangements, which is precisely 5 factorial, and that's 120, right? Yeah, so yeah, this is something from linear algebra, that suppose that A is a real square matrix such that A square is A, in which of the following must hold for A. First, you have both 0 and 1 are eigenvalues of A. Every eigenvalue of A is 0 or 1. A is a 2 cross 2 matrix, and finally A is equal to its inverse. Okay, so we can clearly discard this one out and this one out. So that's easy, because you can just take A to be, let's say, the 100 of 100 cross 100 zero matrix, right? So D doesn't even make sense, and C is obviously false, and this you can discard this one as well, because you can take the identity matrix. 0 is not an eigenvalue of it, and so we are left with this one, and it's very probable that this will be the correct answer, and indeed it is, because you can just take, let's assume that C is an eigenvalue of your matrix A, then there is an eigenvector V, right, such that AV is equal to CV. V is non-zero, so once you apply A square on V, what you arrive at is C square V, and A square is A, so you have AV, which is CV, right? Now C is non-zero, and I mean V is non-zero, and hence this will imply that C is equal to C square, right? And that will give you that C is either 0 or 1. So this means that any eigenvalue of A is either 0 or 1. That's obvious. So you have any questions?
No.
Okay. So yeah, so this is a bit, I mean, it seems to be a bit computational, but it isn't actually. So you are asked to compute you are asked to find out whether this particular matrix, this gigantic matrix, it's a matrix in M3R, whether it is actually invertible over R, that is whether it belongs to GL and R. Okay. Now it's a very basic theorem that the invertibility of a matrix is equivalent to its determinant being non-zero, right? But clearly computing the determinant of such a huge matrix is difficult. So what we can do is we can see the determinant of the advantage of this matrix is that all the entries are integers. So this is in M3Z, and hence the determinant of this matrix will also be an integer, right? So what we just need to find out is whether the determinant is 0 or not, right? So what we can do is we can sort of take the matrix in some M3Zn, where it would be very much easier to compute the determinant, and we can check whether the determinant is non-zero. If it is non-zero there, then certainly it has to be non-zero as a real number or as an integer. So maybe as the numbers appear here, we can just take, let's say, 2 modulo 2, and things are very easy now, because once you reduce modulo 2, the entries become 1, 0, 0, 0, 0, 1, 0, 1, 0, right? And clearly the determinant of this matrix is certainly non-zero, and hence the original determinant is also non-zero. So yeah, yes, this matrix is certainly invertible over R. Yeah, just a moment. How many minutes has it been, do you know? Hello?
No, there is no such timing showing on the screen.
Okay. Okay, so now we come to the 7th question, and yeah, this is actually one of my favorite questions. And so what it is saying is, you are given two maps in opposite directions. So you have G from Y to X and F from X to Y, and you are given that F composed with G is identity on Y, right? So what it, in other words, to just rephrase it in words, what it is saying is that F has a right inverse, right? So you are asked to find out whether F is surjective, F is injective, F is bijective, or none of the above will hold. Now F has a right inverse, that definitely implies that F is surjective, and this is again very easy to see. So you just take, to show that F is surjective, you show that for every element of Y there is some element of X which is getting mapped onto that element. So you just take any little y in Y. So you have to find out some X in X which is getting mapped onto Y. In the only natural way that seems here is to just take GY, which is an element of X. Now if you apply F on this, this is the identity, F composed G is identity, so you just arrive at Y, right? So indeed this relation shows that F is surjective. This implies that F is surjective. Now you can construct trivial examples to see that F is certainly not injective and therefore certainly not bijective. So I mean rather G would be injective because G has a left inverse. Now the interesting thing is that F is surjective, I mean this identity that F has a right inverse implies that F is surjective. This is, the converse of this is also true, that is F is surjective will imply F composed G is the identity on Y, indeed. And one way to show this is just using the axiom of choice, right? So what you do is you have this map, right? So let me erase some part. Okay, this is not what I should be erasing. Let me erase something. So you just have, if this is x, this is y, and if is going from x to y, you are given that f is certainly surjective, right? So what you do is to construct, you just need to construct a right inverse for f, and what you do is you take any element of y here. Since f is surjective, the pullback of, or rather the pre-image set of y is certainly non-empty. In other words, the fiber of f over little y is non-empty, right? So what you do is so you can picturize things like this. So you have y here, and for every element of y, you have a collection of elements of x which map onto that particular element y, right? Little y. So you take another element, again you have the fiber over that element, right? So to construct an inverse function, what you can just do is choose a single element from every collection. From every collection you choose a single element, and to do that you just need the axiom of choice, right? Because you are choosing over an arbitrary collection. It's not a finite collection that you know that you're, this process, this algorithm of choosing will terminate, right? There's no guarantee, so you need the axiom of choice for that. And yeah, so what you are essentially doing is that you are constructing a section of this bundle over y. You have a collection of sets for every point of y. You are choosing a single element from each set, and that will certainly give you a function in the opposite direction, because you are choosing a single element for every little y. So, and you can easily see that f composed G is identity on y. Yeah, so this this is the last one that I have prepared. So as I said, this is just a dry run, and some of the questions are from the week 0, and some are from, just my own inputs maybe. Yeah, so suppose, so this is again a number theoretic question, and you are given this, that suppose f1 is 1 and f2 is 1, and you are given that fn is fn minus 1 plus fn minus 2 for all n greater than equal to 2. That is, this is precisely the Fibonacci series, even though sometimes you start with 0 and 1, but here we are starting with 1 and 1. So what you are asked to do is find out f1022 mod 4, right? So one of the interesting advantages of integers is you can easily pass from the quotient z to, you can easily pass from the group z under addition to z4, and via the canonical projection map. And this z4, as I said, it's also a group, so it has its own addition. In particular, the addition is well defined, right? So you know that if a and b are integers that are congruent to c and d mod 4, let's say, I'll write just 4 here, then a plus b is also congruent to c plus d mod 4, right? So what I'm trying to say or suggest is, instead of computing things up to f1022, you can do that. It's not that you have to compute at each step, you need to go on adding. There is a different way of solving, finding an explicit closed sum expression for the Fibonacci series, right? Using something called the power series method or something. But we don't need to do that. We can just take mod 4 for every fi, right? And we can, and certainly this will repeat after a certain stage. So you take f1 equal to 1, mod 4 it's again 1, you take f2 which is 1 mod 4, you take f3 which is 2 mod 4, you take f4 which is 3 mod 4, you take f5 which is 5 which is 1 mod 4, you take f6 which is 0 mod 4, right? And then certainly you take f7 which is 1 mod 4. So So you understand that it will again start repeating from here. You take F8, which is 1 mod 4, and it will go on repeating, obviously. So the point is it starts repeating after F6, right? So yeah. So F1 is 1, F2 is 1, F3 is 2, F4 is 3, F5 is 1, F6 is 0, and then again it starts repeating. The same sequence starts repeating of remainders modulo 4. So now you want to compute F1022 mod 4, and the obvious way is to just compute the remainder modulo 6, right? So you just divide 1022 by 6, and you just see, I mean the remainder will certainly be 2, because it's apparent that 17 times 6 is 102, so 170 times 6 is 1020, so 2 is the remainder, right? So so that means 2 is the remainder. So once you arrive at F1020, you are essentially coming here, right? That is modulo 4, you are reduced to 0. So if 1020 is 0 mod 4, then if you come to F1021, you get 1, and certainly if you come to F1022, you again arrive at 1, right? So the remainder will be 1. Yeah. So I mean that's it from my side. Do you have any questions?
No.
Okay. So maybe I will stop the recording first and then stop sharing, right? Okay. Just a moment.